So this is a happy occasion. You know, we call them graduate students, and that's because occasionally they graduate. And we're hoping, we don't know, Ph.D. is expected in 2012. Right?
Yeah.
Yeah, that's the right thing to say.
Yeah.
But of course, we reserve the right to make this judgment. Andy graduated from University of California at Berkeley, where he worked with Alex Filippenko, who's also known for his supernova activities, and got a degree in physics and in astrophysics. Then he came here to Harvard, and he got a master's degree. How was the exam on the master's degree?
Not too bad.
Not too bad. There is no exam. All you have to do is obey the law, pretty much, and not get into trouble. That's the degree that Thoreau would not pay for, by the way, as the AM that he was supposed to receive after 5 years of good behavior. Andy won a NSF graduate fellowship and a NASA graduate researcher research program fellowship thing, which have helped him, you know, live high on the hog all these years, and he's now coming to the end of that and moving on to a situation where he can double his income in a single career move by becoming a postdoc at MIT. What you're going to hear about today is that Andy has been wrestling, in his weight class, of course, with a robot. He's been wrestling with a robot for several years, and Andy has won.
Is the webcam on now?
Oh, yeah, let me.
How do we know?
Turn on the mic.
Oh, you mean all of that didn't go out?
Oh, it did. The webcast started 5 minutes ago, so we're good to go. It's all there for posterity. Thank you so much for the wonderful introduction. It's been really fantastic working with Bob. Bob has been an amazing advisor, and Bob was really responsible for making this whole field of observational supernova cosmology possible. And I'm very fortunate to be able to play a small part in this whole enterprise. And I'll talk today about observations of Type Ia supernova explosions that I've done over the past few years with PAIRITEL, which is an infrared telescope located at Mount Hopkins in Arizona. The data set that I'm presenting for my thesis is the largest homogeneous set of its kind. It will nearly double the number of light curves for Type Ia supernovae in the literature in the near-infrared, and it will more than triple the number of individual photometric observations. And the only comparable data set is the recently published Carnegie Supernova Project data set, which is also fantastic work. And both of these sets will become very important for future establishing of the low redshift properties of the sample for cosmology. This is part of an ongoing effort at the CFA to observe supernovae of all types and also to get concurrent optical photometry and spectroscopy. So the fact that we have multi-wavelength data, optical and infrared all together, really enhances the value of this data set. In addition to Bob, I really would like to thank Josh Bloom, who led the efforts to roboticize PAIRITEL. PAIRITEL is the old 2-mast telescope that was used in the 2-micron all-sky survey. And I would have no data if it wasn't for Josh and all the people at Mount Hopkins that led this effort. And I'd also really like to thank Michael Wood-Vasey, who's been my closest collaborator as of late in terms of dealing with the near-infrared photometry. He's now at the University of Pittsburgh, but we worked together when he was here as a postdoc, and he'll be coming in for the defense tomorrow. I really would also like to thank Casey Mandel, because the division of labor in our group, I've been mostly responsible for the observations and the data, the production, and the photometry. Casey's done some really, really amazing work analyzing the data. He's developed some really sophisticated statistical tools to combine optical and infrared data together to measure distances to galaxies and to help us with this whole game of supernova cosmology, which I'll review briefly. Howie Marion has been really helpful at taking over some of the near-infrared observations, and he's a local spectroscopy expert here. Pete Chalice has really been helpful. Ryan Foley is also one of our local experts in spectroscopy. Malcolm Hicken and Goffman and Ryan have been super helpful with photometry questions over the years. Phil Wyatt has been super helpful at getting some of the software we need up and running, which I'll discuss. And I really want to thank all the people at Berkeley who we've gotten the version of the mosaic.
You don't have to, they're not here.
Okay, yes. Fair enough. They've been extremely helpful at setting up an automated pipeline to reduce the mosaics, which I'll talk about. And I've since worked on that a little bit as well. So the big picture, I'll try to review Type Ia Supernova cosmology. I won't be able to review it in great detail. And for the benefit of the non-astronomers in the room, I'll review things a little bit. But definitely, I'm not going to be able to define all the terms, so please forgive the technical jargon. Then I'll discuss the data set, and I'll discuss previous results and some future work. And I'll discuss, we published a previous subset of the thesis data in a paper led by Michael in 2008. And Casey Mandel has taken this data and run with it, and I'm really going to be focusing on his results. I'm responsible for the data, but he's really responsible for the results. So I really want to give him credit where credit is due. So in a public talk, I cannot get away without showing cool pictures of galaxies. And you have to do it. And so the thing to remember is that when a star explodes, it explodes in a galaxy that looks like this. These are Hubble Space Telescope pictures. And we want to measure the distance to these galaxies. So whenever I'm talking about the expansion of the universe, think about a cool picture like this. So we've known the universe is expanding for 70 years or more. But a recent discovery that kind of knocked everyone's socks off was the idea that the expansion of the universe is not only, people thought it was slowing down, but it turns out it's actually speeding up. And this ran contrary to all sorts of expectations. And the way that we can see this, the way the astronomers represent the expansion of the universe is the standard Hubble diagram. Here distance is plotted, and here redshift is plotted. The redshift of an object tells you how much the universe has expanded between the time that the light was emitted by the object and received at our telescopes. And different models of cosmic expansion histories are marked with these different colored lines. It's easier to see in this plot. And the blue line is a universe where the expansion is speeding up. And this is something that was very, very unexpected. The leading candidate for what's causing the acceleration of the expansion of the universe and for galaxies to move away from each other faster and faster and faster is still Einstein's cosmological constant. It's a cosmic anti-gravitational force, a negative pressure force that operates over the entire cosmos. It was a term that Einstein initially introduced in his equations for general relativity as a force to counteract the effects of gravity. This was at a time when we only knew about the Milky Way galaxy, and he didn't know about the expansion of the universe. So when Hubble found that the universe was in fact expanding, Einstein thought that this was a big mistake. And so as an apocryphal story perhaps, he was known to have said that this is the biggest blunder of his career. But this discovery seems to have resurrected dark energy. And the leading candidate right now is that it's a cosmological constant, but people are very interested in the question of whether dark energy is something else, whether it varies in time. And although my thesis data does not answer that question, it helps lay some of the groundwork for things which might help to answer this question. So, as some of you may know, we recently had a very, very exciting thing happen in the astronomical community. The Nobel Prize in Physics in 2011 was awarded for this discovery of dark energy and the acceleration of cosmic expansion. And this is especially cool being here because we have, there's so many connections that lead directly to this from Harvard. So Saul Perlmutter, one of the guys who was awarded the prize, was an undergraduate here. And Adam Rees and Brian Schmidt were both Padawans of the Jedi Master, Bob, in the 1990s. And this is really, really a fantastic thing for astronomy. And in the 14 years since the initial discovery, the acceleration results have been supported by multiple independent cosmological techniques, including measurements from the cosmic microwave background radiation and baryon acoustic oscillations. And here we plot the dark energy density fraction and the matter density fraction. And the thing to note, this is the standard plot that shows this, is that omega lambda is definitely not 0. And that all the results line up and agree, and they're concordant with one another. And that really gives you some confidence. So how did we do this? We used Type Ia supernova explosions. These are exploding stars that explode in distant galaxies. And they're thought to be thermonuclear disruptions of white dwarf stars and binary systems, either by accreting mass from a companion star or merging together. They explode when they reach a certain mass. They're very bright so that we can detect them in distant galaxies. And they're not perfectly standard in terms of their intrinsic brightness, but they are standardizable in the sense that even though their intrinsic brightness varies, we can correct for this. So if we have some estimate of the intrinsic luminosity, we can get the distance from the measured apparent brightness. So when we measure the apparent brightness of the supernova, we ultimately want the distance. To create a Hubble diagram, a number of steps have to happen. We measure light curves of Type Ia supernovae at many wavelengths, ranging from the optical wavelengths to the infrared. We measure the redshift from the spectrum of the galaxy, and then we infer the distances from the observed light curves, plus very, very complicated models that have many, many caveats and use a lot of background information. We aggregate the measured distance and the redshift from any objects, and then we make a Hubble diagram, and then we compare the results to the theoretical model for the expansion history of the universe and the Hubble diagram given by Einstein's theory of general relativity. We constrain the parameters of that model, including the matter density, the density of the dark energy, and W, which is the equation of state parameter, which measures the ratio of pressure to density of the component that constitutes dark energy. And W minus 1 is a cosmological constant. So a lot of people phrase this question in terms of, is W minus 1, or is it something else? Is the time derivative of W non-zero? Does it change over cosmic history? So there are a lot of things that can confound this process. And the biggest thing that can confound measurements of distances with Type Ia supernovae at optical wavelengths is actually dust. So in astronomy, there's always something you're interested in, and then there are a million things you have to get rid of. And then dust is the leading culprit for us. So dust, it does a couple of things. One is extinction. It extinguishes the light from an object. It dims it. And so it's tricky because we know that supernovae have some intrinsic luminosity variation, but when it's dim, we don't know if it's also dim due to dust or if it's just intrinsically dim. Dust also reddens light. It preferentially absorbs or scatters away bluer light. So in the same way that the sunset does, because light is passing through a larger column of air than it is at noon. But there's also intrinsic color variation in supernovae. So when we see an object that's red, we don't necessarily know if it's red intrinsically or if it was reddened by dust. If we ignore dust, we will systematically overestimate the distance because we'll assume it's farther away than it really is. If we measure dust inaccurately, we'll also have a systematic error in the distance. And it turns out that for optical observations, this is perhaps arguably the most important systematic error. Some people will claim that other things are more important, but in an approach where you actually model the physical effects of the dust, it seems to be the most important. The benefits of near-infrared wavelengths, which is really the primary motivation for this whole endeavor, is that near-infrared light penetrates through dust. It's much less sensitive to being absorbed. It's anywhere between 2 and 12 times less sensitive to dust extinction than the optical bands. We also know that intrinsically near-infrared supernovae 1A are better standard candles. It takes less effort to standardize them than it does at optical. We can already make observations at low redshift using instruments like PAIRITEL, which I'll discuss. I should mention that using low redshift near-infrared data alone, we cannot constrain cosmological parameters and dark energy. We need high redshift data for that. And we cannot observe high redshift infrared data from the ground because the intrinsically rest frame light is redshifted to the longer wavelength by the expansion of the universe, so that by the time it reaches our telescopes, it's been redshifted to the long wavelength that's blocked by our atmosphere. There are only a few infrared wavelength transmission windows in our atmosphere that we use to observe ground-based infrared data. We can perhaps do some of this work with HST and in the future with James Webb Space Telescope. This is the Hubble Space Telescope. And this picture is an artist's conception of a mission concept for WFIRST, which is a proposed NASA mission to study dark energy with Type Ia supernovae with an infrared and optical telescope. So this is a light curve of a supernova. It's something that rises in brightness and fades over time. This is an image with the host galaxy light removed. And this is what we're talking about when we're talking about what we're measuring. It turns out that infrared light curves and optical light curves have different characteristic shapes. Infrared light curves have this double-peaked or Bactrian structure, and optical light curves have a more dromedary structure. And we see this, the second peak in the near-infrared coming into play a little bit in the R band, definitely in the I band, which we still consider optical, although the borderline is arbitrary. It's definitely very, very prominent in the J band and H and K as well. So when it comes to standardizing the light curves, this is what we mean. If you look at the optical light curves, for example, in the B band, they have a range of intrinsic brightness. This is brightness versus time. And so they're not perfectly standard. They would be perfectly standard if there was no spread up here. But it turns out that there are properties that we can measure which do not depend on the distance, which correlate with the luminosity, which we can use to infer a way to correct for the fact that they don't have the same intrinsic brightness. It's a simple one parameter, for example, a stretch-like parameter that you can perform to get down to this plot where they all line up with very, very small intrinsic scatter. And that ends up being a very, very good standard candle after standardization. In the near-infrared, things are a little more complicated. You can't really use a single parameter model to do this. So Casey has developed a model where 4 parameters govern the J-band light curve shape, and you can do something similar where you can standardize things. However, what we now know from aggregating the near-infrared sample included in my thesis with other supernovae from the literature, the Carnegie Supernovae, is that the near-infrared data are really, really quite standard, especially near the first peaks. You can see this in the residual plot a little more clearly. And in fact, they're so standard that even without any near-infrared light curve shape corrections, you have a scatter of magnitudes essentially as good as optical light curves after light curve shape corrections have been applied, so that you can actually play the game of measuring distances even without doing light curve shape corrections. So given this, the goals of the thesis project are to study a large near-infrared set in a homogeneous way of ground-based data, do this concurrently with optical observations, and as Casey's results have shown, we can get more accurate and more precise distances. It'll help us understand dust in other galaxies. It'll pave the way for future high redshift cosmology with maybe the Hubble Space Telescope or a mission like WFIRST. And the thesis itself presents this very large homogeneous data set. The sample of infrared light curves that have been published is around 120. My thesis will publish about 100 more, and so that will almost double the sample, and it'll more than triple the number of individual observations. So now I'll discuss the data set more specifically. So PAIRITEL is the 1.3 meter telescope at Mount Hopkins. That's what I've been using for all of this data. It was roboticized in 2004 by Josh Bloom and collaborators. It's an autonomous Q-scheduled observatory so that we can submit requests to observe given objects, and the Q-scheduler decides. There's many different PAIRITEL projects. It decides which ones get observed. One of the drawbacks of this is that you cannot guarantee that any given object will be observed on a given night, but it's more than made up for by the sheer quantity of data that we're able to get. We've been fortunate to write proposals and be awarded almost 30% of the time on this telescope since 2005. This is a ridiculous amount of data. This is 6 months on the sky, and this is unheard of in the sense of many students who are at other institutions that aren't as fortunate with the observational resources that we have here have maybe 4 nights on a telescope for their entire thesis, and maybe 2 of those nights are washed out due to bad weather. And so I'm swimming in data, and I this creates other problems which I'll discuss, but they're better problems. So we have a large homogeneous data set with a well-tested camera. Since we're using the transplanted 2-mast south camera that's been moved to the 2-mast north telescope, which became PAIRITEL, we get simultaneous observing in the J, H, and K near-infrared passbands. We can observe objects almost every night. Naturally, the photometric calibration is from 2-mast because we're on the same telescope and system. And that's really great. We don't have to correct our natural system to 2-mast because we're already on it. And this is all part of a larger program of getting optical photometry and spectroscopy, also at Mount Hopkins, which really enhances the value of the data set. So, as Bob mentioned, PAIRITEL is a robot, and I've wrestled with it, and sometimes lost, sometimes won. And the scheduler is fantastic in terms of what you can do. The thing about this, which is really interesting, is that it allows me to be, a lazy astronomer, being able to tell the telescope what to do and do astronomy from the discomfort of my office chair. But the truth is that there's a little more to it. You actually do have to constantly engage in effort and monitoring in order to really make sure things are being done right. We're not discovering these objects ourselves, so we're following up on optical discoveries, let's say by the Observatory Supernova search or amateur astronomers. So we have to pay constant attention to the circulars to find out which new objects are interesting and worth observing. We have to decide which ones to put in. There's also spectroscopy being done locally. Many of the supernovas are spectroscopically typed by our group, so that we incorporate that information to say, okay, there's a supernova that was discovered 2 weeks after maximum. Maybe we're not interested in following that. We want ones that are discovered closer. Or maybe it's a Type 2 supernovae that we're not currently prioritizing. Even though it's a robotic telescope, there's a lot of effort that's required to manage things. So for example, here's just a snapshot of the web page I maintain to keep track of the database of all the observations. And we have, this is since it was commissioned back in 2004, I kind of became involved in 2006, and Mariam Mogjaz was very helpful at the very beginning. We've observed roughly 15 to 20 supernovae per year that are bright enough to observe and at the right viewing windows for our telescope. We also observe supernovae of other types. They're not included in my thesis, but I have done the photometry and reduced things in exactly the same way as for the 1As. So, what are the biggest problems with near-infrared astronomy? The answer is the sky. The sky is the enemy. The sky, this is a picture, for example, from the 2-mass H-band at Mount Hopkins of the H-band sky. And this is what we have to deal with. If you had infrared eyes and you walked outside at night, the sky would be glowing. So how do you do astronomy under those circumstances? You can't do astronomy in the daytime, at optical astronomy, for example. And and also there's this little feature here, which is just some problem with the detector, bad pixels. How do you get rid of that? Turns out that the answer is to take multiple small exposures. These are 8-second exposures, 3 of them stacked together, and also move the telescope around on the sky. And I'll explain why that's important. The problem is that the near-infrared sky is so bright it can saturate the telescope in 10 seconds. And if you want to observe really faint objects, let's say faint supernovae that require, let's say, 30 minutes of exposure time, you have to combine multiple exposures together and turn them into a mosaic. So we take a bunch of small exposures and combine them into a wider field mosaic. The code that does this was originally developed by Josh Bloom, Colin Blake, Dan Steyer, and Chris Klein at UC Berkeley. And they have a really fantastic setup where they automated nightly reductions so that we submit objects. We get an email from the friendly PAIRITEL robot in the morning that says, your images are ready. You go look at them. And then you say, OK, oh, this image looks great. Then you say, OK, this image is terrible. The pointing was off. The supernova is not even in the field. The mosaicing failed. But it works really, really well. And it's an incredible time saver and resource. And recently, there were some new updates to the code that we needed for the supernova data. And Bill Wyatt helped me get a version of the code running locally so we can make our own mosaics and incorporate the upgrades that I was able to write. So I'm motivated why you want to combine multiple small exposures to get a larger effective exposure time. But dithering, moving the telescope on the sky, also helps you in a number of ways. One of them is, and you can see these little gray features. Those are representative of bad pixels, like you saw earlier on the camera. Dithering on the sky, allowing different light from the sky to fall on different pixels of the detector, allows you to easily identify these objects, these bad pixels, and remove them. That's really important. In addition, dithering helps you to estimate the sky and subtract it out, because that's the thing you're not interested in. One way you can do this is by taking a time series of unregistered dithered images and take a pixel by pixel median or weighted average through the stack. And that because most of these pixels will be hitting skylight over the course of the dither pattern, it ends up being a reasonably good estimate for the sky. So this is a picture of some mosaics in JH and K. These are the sky mosaics that my new updated mosaic code creates. It's the thing that we added to the mosaic pipeline. The camera itself, it's an infrared detector. It's cooled down cryogenically, but it's still warm, and so there's still thermal emission in the detector, which creates false counts called dark current. PAIRITEL doesn't have a shutter, so we don't measure this independently. It's lumped together with the sky counts. These are all background counts that are things we want to remove, and we're not interested in. The thing that's important is that when you go from J to H to K towards longer wavelength, these are the median number of counts in the image. You go from, let's say, 800 counts to almost 20,000. Things are much worse in the K-band. K-band is really difficult. And this underscores the difficulty in making measurements there. And you can see it up here, too, where even after the sky has been removed, there's still a lot of residual variance. And that makes it very, very difficult. Another thing that we want to get rid of is the contribution of the galaxy light. So here's a supernova. There's a picture of the galaxy, which we image 6 months to a year later. And we subtract out the galaxy light. This is residual masking from the galaxy. This is residual noise from the subtraction. Ideally, all you have left over is just the supernova light. We make measurements of the brightness of that light, and we make our light curve. The truth is the process is a lot more complicated, and there's some problems with our detector is not a high-resolution detector. It's undersampled. Its pixels are very big compared to the typical seeing disk of point sources, so that when you do galaxy subtraction, you have to match the images to the same PSF, convolve them to the same seeing, and it's very difficult to do that with an undersampled detector, so that we know that galaxy subtraction is going to systematically, for a given subtraction, take away a little bit of flux or add a little bit of flux to this subtraction. And so the best way to get around that is to observe multiple template images, anywhere from 2 to 10 for a given object, and make a subtracted light curve for each of them and average them together. So we see that here, where we see light curves, and the spread indicates points from different subtractions. And as you can see, as things get fainter, the spread gets larger, which makes sense because it's more difficult to do subtraction for fainter objects. And that we combine these together, and then we include the additional uncertainty from the subtraction process in the larger errors that you see towards later times. And we can always benefit from getting more templates, and the nice thing is that the host galaxy is still there even after the supernova is faded, so you can go back and get as many templates as you need, and this is one thing that's really nice with a robotic telescope. So we've got ridiculous amounts of data. Here's a mosaic of J-band mosaics for 120 supernova 1A fields. We have 3 band passes. We've got roughly 35 light curve points on average. That's almost 15,000 images. So if you want to do photometry on these, photometry is not a simple point and measure the brightness. It's a very sophisticated pipeline. The pipeline we used was developed for the Essence project and Supermodule projects by Armin Rest and collaborators, and it's computationally intensive. The galaxy subtraction is computationally intensive, and so we need a really, really big computer. Here is my infomercial for the Harvard Odyssey cluster, which has helped solve this problem for us. So this is a supercomputer that uses a whole bunch of conventional computers networked together. It's got over 13,000 processing cores. And the thing that's really fantastic is that with resources like this, so I was able to write code to partition the photometry pipeline into all its computational subtasks that can, in the smallest amounts that they can be partitioned down to, and submit it to the Odyssey queue system. It'll send it out to various nodes and execute everything in the right order. And so we can now rerun photometry on all of our objects essentially overnight, 5 to 7 hours, depending on node availability, compared to the setup that we had in the paper, the Woodvasio 08 paper we published several years ago. That would have taken 3 weeks, a month, something like that. So this is really, really, really amazing. And after spending so much time inside the Odyssey cluster dealing with all the code, I can tell you that it definitely looks like this on the inside. And if it keeps assimilating new nodes at a rate like this, it's going to look like this in a couple of years. I'm very, very happy with the Odyssey cluster, and it's just amazing to have computational resources like this. So here are the light curves that we published, 21 light curves in 2008. The gray strips are templates, which are sort of the average light curves. So all of these are sort of normal light curves. The ones in red are ones that are peculiar. These are the ones that you do not want to include in your Hubble diagram. These ones are not the same kinds of objects, so they're not standardizable candles in the same way. We've made a whole number of improvements to the photometry so that my thesis actually is going to publish revised photometry for those same objects that we published 4 years ago. There are always things that you can improve in photometry, so it's very, very, it's often standard to produce revised results that way. We published 1,000 individual observations before. There's going to be somewhere between 9,000, maybe 10,000, 13,000 images that we were able to do photometry for this set. We have better mosaics. We have noise maps that we incorporate. The new pipeline that Chris Klein and others built at Berkeley, 15 to 20% more mosaics actually succeed, so we're actually able to publish more data for the same objects that we published before. In addition, we've changed the photometry pipeline around so that 20 to 40% more images succeed through the photometry pipeline. So we actually have a lot more data even for the same objects. We have a better method for galaxy subtraction for our data. We have a better understanding of our uncertainties. And the Carnegie Supernova Project happened, even though it's in the southern hemisphere and we're in the northern hemisphere, happened to observe 19 objects that also overlap with our set, so we can do a comparison photometry as a good external consistency check. So here's the thesis data set at a glance, over 100 light curves with fits shown. Some of them are very, very well sampled. Some of them are very faint and noisy. The paper that we're going to publish will ultimately make cuts and decide, okay, we're going to include these guys, we're not going to include some of these guys. But we have a really, really large data set. And we have concurrent optical photometry for almost all of these. There's an additional 9 others that weren't shown on the previous plot. These are peculiar 1As. You can see they're all very different from the template. These will be published as well, but they're not going to be included in any analysis that, for example, Casey will do with Hubble diagrams. Here's just kind of a zoom in of some of the better sampled ones that we have. So, typical, yes. Okay, yeah. Yes, I'm trying to be honest, but yeah. And speaking of honesty, I'm going to point out some limitations of our data set and give some credit to Carnegie as well. So in comparison with the Carnegie set, we do have more supernovae that we're going to publish. They had a couple papers where they published around 74, 75 type 1A near-infrared light curves. They have Y-band data, and we have none of that because we don't have any Y-band instruments at Mount Hopkins. But this data set is going to publish significantly larger numbers of J, H, and K observations. And especially in the K-band, the Carnegie set has very, very few observations. And so in the same way that they have the Y-band data are covered, we have a growing K-band sample. Even though it's very difficult to make K-band measurements, we have a lot of K-band data. The Carnegie uncertainties are typically 2 to 3 times smaller than our uncertainties, but this is because of things that we understand. They have a higher resolution camera. They also have the ability to use a 2.5 meter telescope to observe some of the fainter targets. When they do host galaxy subtraction, this undersampling of the detector and the PSF matching between subtracted images, it really hurts us. And it doesn't hurt them in the same way, so that we know that galaxy subtraction is going to give us larger errors overall. But the sheer quantity of our data makes it extremely useful. These are both very complementary data sets. Most of the objects that we observe are different from what they observe. And both of these data sets together will kind of form the benchmark set for the low redshift objects. So here's just a few comparison photometry plots. There is scatter, but that the mean differences are consistent with 0. Some of it is just due to problems with the limitations of the model fitting. But I've done tests which show that our photometry agrees, and it agrees in a way that's a lot better than what it did 4 years ago. So what can you do with this data? So in the 08 paper led by Michael, we made Hubble diagrams using the H-band data alone, making the assumption that H-band data are perfect standard candles, which is actually not a bad assumption. And the scatter in the Hubble diagram was only 0.15 magnitudes, which was comparable to or better than the scatter from, let's say, using Sarabjah's MLCS to standardized optical light curves. The nice thing that we found is that if we combine all the supernovae at the time, there were about 40 at the time, including 18 from PAIRITEL and 23 from the literature, the distributions of absolute magnitudes were consistent with one another. And even though we now know there were some problems with the Wood-Vasey photometry, the mean measurements of the absolute magnitudes still were not systematically different from the literature. We also showed that the Hubble diagram residuals don't seem to have any correlation with optical light curve shape as parameterized by the MLCS parameter delta or optical extinction. So here are again the new near-infrared template light curves. And again, things you can do with them are exclude peculiar supernovae from the sample by seeing how different they are from the template. For objects that are well sampled, you can do light curve fits. And in astronomy, colors are the differences between two light curves. And so, for example, if you look at the optical minus infrared colors, in this plot, the objects that have the most extinction and reddening, and their colors are redder, are moved up in the plot. So, for example, here's a very, very highly reddened object. This line represents the fiducial set of unreddened objects, which we use, for example, a subset of supernovae that have independent evidence for having very little extinction by dust. And the offset tells us the color excess, which we can use to estimate the amount of extinction by dust. And that this is very, very, very important to have infrared data involved in this because it's much, much easier to measure. What Casey has done is he's developed this very, very sophisticated statistical model that takes as input multi-wavelength light curve data and in a hierarchical Bayesian framework is able to condition on the parameters of the host population of supernovae, the parameters of the dust distribution, extinction distribution, the intrinsic colors of supernovae, and to output posterior inferences for the most high probability extinction, host galaxy dust loss slope. And for example, here you can see that the optical extinction of, let's say, 0.13 magnitudes is much, much larger than the infrared extinction in the H-band. And this is a very, very powerful approach. And the thing that Casey has shown, which is really fantastic, is that this is the promise of including near-infrared data with optical, is that if you include near-infrared data with optical data together, you get more precise and more accurate distances. The more accurate distances can be shown on the top, where the blue is if you just have optical data. The green is if you add in the RI band. And then the red is if you include the infrared data together. And that the black line represents the distance that you would get from the Hubble law, which is valid for low redshifts in the nearby universe. And so in both cases, including near-infrared data helps you get a more accurate distance. But in addition, it gives you a more precise distance by shrinking the uncertainty contours in the distance by going from optical to including more longer wavelength and more infrared data. You can make Hubble diagrams like this. And so this is Casey's Hubble diagram. And if you have optical only with his method, which is called Bayesian, the scatter in the Hubble diagram is 0.15 magnitudes. And if you include near-infrared data, this is 0.11 magnitudes. And so, as expected, you do a lot better. So the big picture is that this data set, we've already been able to show that they're Type Ia Supernovae are very, very standard, especially in the H-band. They're more standard than optical data, even after light curve shape corrections. You can see that in the more sophisticated analysis that Casey did, the near-infrared H-band seems to be the most standard, so that's a very, very promising wavelength for future studies. And that combining near-infrared and optical data together is really, really an excellent way forward. In the long term, what you can do with this information about the near-infrared population of supernovae is you can learn more about the distributions of dust, extinction, and intrinsic color. And even without including near-infrared data in the Hubble diagrams for cosmology, this information alone already really, really helps you to constrain the priors which people use in cosmological fits. Eventually, we want near-infrared data at high redshift as well. And we might be able to get that with the Hubble Space Telescope and J-band, for example. And eventually, if W first, or whatever it ends up being called, launches, we will have a really, really fantastic instrument to measure dark energy directly. And so for now, the hope is that this data set will lay the groundwork for some of these eventual projects and play a very, very small but still helpful part in this whole mystery of dark energy. And I'll end just by acknowledging many, many people. I'd like to acknowledge Bob again and my thesis committee as well. I'd like to acknowledge many collaborators, and especially I'd like to acknowledge the people at Mount Hopkins who really are dealing with the telescope and fixing it and all the mechanical problems. This is something that I've had absolutely no part in, and I'm so lucky. I'd also like to thank Josh and Ramesh, who were my advisors to my earlier projects that Bob was mentioning, where we had no exam. And, well, we had an exam, but I'd like to thank the astronomy faculty here. I'd like to thank my postdoc sponsors at MIT. I'd like to thank the administration here, Peg, Jean, and Donna. You know that I've already given the spiel for the Odyssey cluster, so they're fantastic. And the computing facility people here have been fantastic too. I'd like to thank the NSF and NASA for giving me money for some reason. And thank you so much to fellow grad students and friends. The one thing that's really cool about this department, as opposed to many other departments around Harvard, is that people really love to help each other, and people are really collegial, and people generally are hard workers and laid back, but you know, really treat each other as human beings, you know, not only as abstract intellectual entities that are just there to output stuff. And it makes it makes it really fun to work here, and I've really enjoyed being here. I'd like to thank my family for their love and help and support. Thank you for flying out from California and Toronto. And last but not least, I'd like to thank my fiancée, Kristen, who's put up with so much during this thesis finishing process. I love you. Thank you so much for supporting me. And I'm so glad that it's almost done. All right.
So I guess we're ready for questions. Are there questions? Yes, over there in the green shirt there that says Hawaii.
So why are the near-infrared light curves so much less? Why do they have less scatter? Is it just the dust things that you talked about, or is there some astrophysical reason?
Didn't I tell you something?
Oh yes. One of the reasons they're intrinsically more standard. This is definitely not my area of expertise in supernova explosion.
Oh, I think it's someone. Excuse me for a second.
Okay. All right.
Hello? Somebody from the webcast? Just a minute. Let me put you on speakerphone here. Speak up. You can't see the webcast? So how could you ask a sensible question? You're familiar with the field? Just a minute. It's somebody from England. Who would that be? Just a minute. Can you see the button that has the speaker on it? Is it this one? Is that it? Uh-oh. They cut one. Go ahead. Go ahead, Casey. Go ahead. Everybody's waiting. Yeah, ask your question. We'll get back to your question in a second. Sorry. Yeah, this is costing me money. Oh, it's costing you money. Oh, all right then. Go ahead. Take your time. Here. You repeat the question. That way
Hey, Casey. Hey. Yeah, you want to ask me the question, and then I can repeat it for everyone? Oh, okay. He was hoping you could repeat it.
Oh, for heaven's sakes. All right. Let's get on with it. It's a good joke, but, you know. Okay, fire away. Congratulations on completing a very valuable set of data. Yeah. But the question is, yes, go ahead. How soon can you send me the data? Oh, that's a fair question. All right. Thank you, Casey. Will you take your answer offline? No. All right. Go ahead. Just give him some bland kind of vague.
The data will be publication ready, most likely in a couple of months in April, and at the time of submission, that's I think the best time to give you the data because it'll be in good shape.
Did you get that? Oh, he says we'll talk about it. Okay, we will talk about it, I'm sure. Okay, thank you, Casey. And now we're going to answer the question of the people who are actually here. Okay, thanks, Casey. Bye-bye. Okay, woo! How was that for exciting? Okay, now you have to answer the question. The question is...
Why are they intrinsically more standard? And again, this is definitely not my area of expertise, but the emission is dominated by reprocessed radiation from iron line elements. And it turns out that if there's a larger increase in bolometric energy, it ends up getting reprocessed into the near-infrared in a way where there's sort of a thermostat effect. And so this ends up compensating for the fact that the brighter objects end up having a certain fraction of their emission in the near-infrared, and the intrinsically dimmer objects, bolometrically, end up having a larger fraction that's emitted in the infrared. And so the real expert is Dan Kaysen, who's developed some models of this, and that his work shows that intrinsically you do expect the near-infrared radium H-band to be the most standard. And it was nice that that's what we found in the data as well.
Yeah, Avi. Yes. You're looking quite old. Oh, sorry, go ahead.
Given that we know the cosmological parameters by now to a few percent, at best 5%, at worst 10%, can you set constraints on the level of intergalactic dust using your data? Have you tried to do that?
I have not thought about that at all, but that's an interesting question. The things that we're mostly thinking about are dust in the supernova host galaxies themselves. We actually could place very, very, very good constraints on that. But generally, when we're doing our analysis, we're including Milky Way dust, and we're including dust in the host galaxy, but we're not thinking so much about intergalactic dust.
Intergalactic dust will have an increasing effect as you go to higher redshift. You should see a trend with redshift that cannot be explained by intrinsic.
Oh yes. Well, our data set alone is just a low redshift data set, and so that we really can't answer that question quite yet. But certainly with high redshift data from HST or JWST in the future, this is definitely something that could be answered. And that there are tons of things that can be done once you have this tool to increase the precision of distances, completely independent of cosmology. And it's very, very good to think about all the other applications.
Yeah, go ahead.
Do you know what the peculiar type one is in your type R? I mean, why are they peculiar?
Well,
Are they really type 1As?
this is still an ongoing question, and it could be that there are many different ways to produce a 1A. Maybe the most common are the single degenerate scenario where you have a white dwarf accreting mass from a companion star. It accretes up to near the Chandrasekhar limit of 1.4 solar masses and explodes. Another scenario is where you have two white dwarfs merging together. One of the leading thoughts is that perhaps some fraction of the peculiar supernovae are due to these different routes. It also could be that the compositions of the white dwarfs are different. A helium neon and a carbon oxygen white dwarf explosion could be very, very, very different. At the level of including them in Hubble diagrams, one of the things that's nice is that even if we don't know any of the supernova physics, and even if we don't have spectra, just based on light curve morphology alone, we can exclude them from cosmology. So it's a great question if you're interested in what makes up Type Ia Supernovae as a physics question. But that's not something that I've been particularly working on. But it's definitely one of those things that it's nice that you don't have to know the answers to that question to still use them for cosmology. So that
Throw them out.
Yes. So people, but it's always a worry that if you have a set of objects which you're thinking of as standard candles, you don't want them to be contaminated by other objects.
Yeah, go ahead.
So a question about the supernova themselves.
Mhm.
You mentioned the case models earlier, and in his models, the second peak of the infrared that seems to run with J-band is due to propagation. And so it seems to me that the timing and magnitude of this J-band second peak is extensive of the iron reduction and the contributed itself. So how do you look into, because you have this multi-parameter like your model, look into whether the parameters of this model are correlated with other properties of the supernova
I have not done that, but that's something that I definitely have talked about doing with Howie. Howie has built up a set of near-infrared spectra as well, and that one of the things that you could do is, for example, look for correlations between the near-infrared light curve features like the J-band second peak, and try to see if you actually see the signatures of this iron ionization transition in the spectra, and that's something that is a very, very strong next step that can be done. There's also I mean, in terms of not just about the supernova themselves, there's some indication that there are other features that correlate with luminosity from the spectra. Stephen Bailey and Casey and Stefan Blondin have looked into this for supernovae as well, and that the answer is that there seems to be some correlation between those features that can help you standardize the distances as well. So that this looking for correlations between the spectral features and the light curve features can help you both understand the supernovae themselves and also potentially further standardize the candle too.
Okay, well, if that satisfies your curiosity on all aspects of this, I think we should give Andy another hand. Because he's going to need that boost of confidence for his real examination.
Yes, yes.
Thank you.
Thank you.
Good.
Thank you.
Very good. Very good. Many people wish that they could go to a place where they had so much ability to get data and analyze it.
Yeah.
Oh, we do.
Oh, thank you. Thank you. Thank you.